All right, welcome. Today we are going to get our hands dirty and go on a bit of an assembler's journey. We're going to build a foundational NLP pipeline, starting with raw, messy, chaotic text and transforming it step by step into the clean, structured data that a machine can actually understand. So let's build this thing from the ground up. So here's our blueprint for the day, our schematic. We'll start by going from chaos to a proper corpus. Then we'll run a sanitization pass to clean things up. After that, we'll dissect the anatomy of a sentence, find the lexical root of our words, engineer some features, and finally, we'll get to the vector transformation. Let's get started. Okay, section 1, from chaos to corpus. Look, before we can build anything, we have to understand the raw material we're working with and all the challenges that come with it. So take a look at this. As a human, you get it instantly, right? You see a link, you see someone being mentioned, and you feel the enthusiasm. But for a machine, this is just, well, it's noise. It's a jumbled up string of characters where URLs, punctuation, and even that smiley face have no built-in meaning. And that really brings us to the central question of this whole explainer. How do we translate this messy, nuanced human language into a format that a computer can actually work with? The entire pipeline we're about to build is the answer to that very question. Let's start with the basics, our fundamental unit of work, the document. All this is a single piece of text. It could be super short, like a text message, or a single sentence from a report, or it could be massive, like an entire novel. Now, when you get a whole collection of these documents together, that's what we call a corpus. It actually comes from the Latin word for body, and that's a great way to think about it. This is the entire body of text that we're going to feed into our assembly line. Section 2, the sanitization pass. All right, now the real work begins. This is our first active station on the assembly line, where we do the initial cleaning and strip away all that obvious noise. So why even bother with all this? Well, you've heard it before. For any model, it's garbage in, garbage out. If your data is noisy and messy, your model's accuracy is going to suffer, period. And you got to remember, this isn't a one-size-fits-all kind of deal. The exact steps you take and even the order you do them in really depends on the specific problem you're trying to solve. Here are some of the most common stations on our cleaning line. We usually start with lowercasing, just to make sure that the with a capital T and the with a lowercase t are seen as the same word. Then we start stripping out things that are just for humans, like HTML tags and URLs. We'll get rid of punctuation. And finally, we often remove something called stopwords. Let's zoom in on these stopwords for a second. These are those super common glue words, like the, is, in. They don't often carry a lot of unique meaning on their own. By removing them, we help the model focus on the words that are actually important, the ones that carry the real signal. But, and this is a huge but, here's a key engineering decision for you. You don't always remove them. For something like spam classification, yeah, you absolutely apply removal to focus on the content words. But for machine translation, no way. You need those stop words for correct grammar and sentence structure. The big takeaway here is clear. Your final goal dictates your strategy. Okay, section 3, anatomy of a sentence. So our text is clean. Now it's time to deconstruct it. At this stage, we're going to break the text down into its fundamental components. This process is called tokenization. It's simply the act of splitting a string of text into a list of smaller pieces, which we call tokens. Honestly, this is one of the most fundamental, foundational steps in all of NLP. It's how we go from an unstructured string to a structured list we can actually work with. So remember this one. Now, we can tokenize at different levels of detail. Word tokenization is probably what you think of first, but we can also do character tokenization, breaking words down into individual letters. And then there's subword tokenization, which is this really clever middle ground. It breaks words into meaningful parts, like prefixes and suffixes. This is awesome for handling rare words or words the model has never seen before. This all seems pretty easy, right? Just split the text by spaces? Well, not so fast. It gets really complex. Many languages, like Japanese, don't even use spaces between words. And what do you do with something like $100? Is that one token or two? These are the real engineering challenges that a good tokenizer has to solve. All right, so we've cleaned the text and we've broken it into tokens. Our next station on the line is all about normalization. The goal here is to standardize our tokens so that we can treat all the different variations of the same word as a single concept. So here's exactly what I mean by normalization. To a machine, connect, connected, and connecting are three totally different words. We need to reduce them all down to a single root concept: connect. This makes our vocabulary much smaller and helps the model generalize better.
One way to do this is called stemming. Now, this is a pretty crude but very fast approach. It basically just uses a set of rules to chop off the ends of words. It has no idea about language or grammar, it's just a simple algorithm. And because of that, the result, the stem, might not even be a real word you'd find in a dictionary.
Let's take a quick peek under the hood at the most famous example, the Porter stemmer. It just works through a series of rule-based steps. It has rules for plurals, so caresses becomes caress. It has rules to chop off common verb endings like ing. And it has other rules for different suffixes. It's really just a simple step-by-step process. Now, the more sophisticated cousin of stemming is lemmatization. Instead of just blindly chopping off endings, lemmatization actually uses a dictionary and analyzes the word's structure to map it to its true root form, which is called the lemma. The key difference? The output of lemmatization is always a valid, meaningful word. So, this brings us to another one of those key architectural decisions for an NLP engineer. Stemming is fast and simple, which makes it great for things like search engine indexing, where speed is everything. Lemmatization, on the other hand, is slower because it has to do dictionary lookups, but it's much more accurate. That makes it better for applications like chatbots or machine translation, where getting the language right really matters. It's that classic speed versus accuracy trade-off. So how can we actually measure the impact of all this normalization? Well, we can use a metric called the type token ratio, or TTR. It's super simple. It's just the number of unique words, we call those types, divided by the total number of words, or tokens. This chart makes it pretty clear what TTR tells us. A high TTR means you have high lexical diversity, lots of different words. A low TTR means the text is pretty repetitive. Now, after we run stemming or lemmatization, our TTR should drop, and that makes sense, right? Because we've collapsed a bunch of different word variations into single roots. Section 5, engineering the features. Okay, we've cleaned, tokenized, and normalized our text. Now we have to prepare it for the machine itself. And here is the fundamental reason why this next step is so critical. Machines are number crunchers. They live in a world of vectors and matrices. They don't understand words. Our text, even as clean as it is still not in a language they can speak. And so, we have to perform what's called feature engineering. In the world of NLP, this is also known as text representation. It's the process of converting our nice, clean list of tokens into a numerical format, a set of features that a machine learning model can finally understand and learn from. This is the bridge that takes us from language to mathematics. We have arrived at the final station on our assembly line. This is it. This is where we take our processed tokens and we package them into the final, standardized product that can be shipped directly to a machine learning model. And that product is the vector. Let's just walk through a really simple example to see how this works. Imagine these 3 movie reviews are our entire corpus. We've already cleaned and tokenized them. Now we have to turn them into numbers. We'll use a classic, simple technique called bag of words. So with the bag of words technique, the first thing we do is build a vocabulary of every single unique word in our corpus. Then, for each review, we just count how many times each word from our vocabulary appears. You can see the results right here in this table. And there it is, the final transformation. That row of counts for review 1, that is its vector. The sentence has officially become a list of numbers. We've done it. We've successfully converted text to a machine-readable format. Our product is fully assembled. But before we wrap up, let's just pause and think for a second. We've successfully transformed language into something a machine can use. But what did we sacrifice to get here? The name bag of words is a pretty big clue. We've literally treated the words like they were just thrown into a bag. And in doing so, we've lost all information about their order, about grammar, about context. Is very scary movie the same as scary very movie? To this model, yeah, it is. And that limitation is the perfect jumping off point for more advanced techniques, leaving us with a really critical question for our next journey.